All right, let's look over a review for exam 3 for Math 1030 and Math 1035 at Salt Lake Community College. These are the modules for statistics, that is gathering and describing data, and also probability, simple probability, sums, products, and also the two-way tables and expected values. Starting off with statistics. Question number 1 of the review. A political scientist surveys 22 of the current 107 representatives in a state's legislature. What is the size of the sample? What is the size of the population? So the population is a large group. In this case, that population would be 107 representatives. And the sample is a subgroup. In this case, it's the 22 that the political scientist surveyed. So the size of the sample is 22. The size of the population is 107. All right, question number 2. The city of Raleigh has 9,900 registered voters. There are 2 candidates for city council in an up-and-coming election, Brown and Felice. The day before the election, a telephone poll of 350 randomly selected registered voters was conducted. 109 said they'd vote for Brown, 218 said they'd vote for Felice, and 23 were undecided. The question, describe the population the surveyors are really interested in. Okay, so these surveyors are surveying for an election. So they care about who is voted in for the election. So if we look at these options, all citizens of Raleigh, no, they don't care about the people that don't vote or can't vote. All registered voters, yeah, that's who they're interested in. All registered voters. All registered voters who with telephones, that's actually who they're finding out about, but that's not really who they're interested in. The fact that they are doing this poll via a telephone poll means that they have built-in bias in their sampling technique, that they're not actually finding out about all registered voters, they're only finding about the registered voters with telephones. So it's not going to be very representative. Built-in is called a sampling bias. 350 voters surveyed, that's the sample. 109, that's a statistic in the sample. So the correct is all registered voters in Raleigh. Question number 3. In a study, the data you collect is habits on an always, sometimes, never scale. So they ask you a habit and you say it's always, sometimes, or never. You can't measure sometimes or never or always per se. This is qualitative data. If they wanted to know how many times a week, then you could actually measure how many times. But is it, or do you always, sometimes, or never? This is qualitative. In the study, the sample is chosen by asking people on the street. Oh, they're asking people on the street. Simple random? No, they're not randomly choosing a group of unnamed people. They're asking people on the street. This is a convenience sample. This next question has a better review of this material. Match the name of the sampling method descriptions given. That's a weird way to say that. Asking people on the street, that one is convenience. Dividing by population by voting precinct and sampling everyone in the precincts selected. Precincts, this has a couple of weird spelling issues and grammar. Dividing the population. So dividing stratified is divide. You divide, you have been stratified. So it kind of has a nice ring to it. Divide, stratified, sort of rhymes. So the stratification method is when you divide a population, but there's 2 of them. Let's see. There's two of them that have dividing. This is separating all students as well. So the difference is here we're dividing the students by grade level and selecting a sample of each grade, whereas here we're dividing the population by precinct and then sampling everyone. This is the big key. They're both dividing, but this one is everyone and this one's just a sample. So dividing the population and then sampling everyone is the cluster. It's a specialized form of stratification. If you just divide them up into strata again, but select a random number from each one, so you select some from each strata, then that's stratified. So this one's stratified, where you divide them up, but then select a few from every division. And this one is cluster, where you divide them up, and then you sample everyone in one of the divisions. Choosing every fifth person on a list, that's a system, systematic. And finally, a number, every name on a list, use a random number generator. That one's the simple random. Okay. Which source of bias is most relevant for this situation? A human resource official conducts a survey asking people if they have ever purchased a personal item over the internet during company hours. Well, they're probably not going to answer to a human resource official truthfully if they have. So if this were a random poll, they might say, yes, I have, but not if they're answering to someone that could get them fired. So this would be a perceived lack of anonymity, as if you're not feeling safe to answer correctly, or truthfully, not correctly, truthfully. Here's another one. Which source of bias is most relevant for this situation? A research study funded by Animal Rights Coalition finds that 85% of adults dislike real fur coats. So if they talk about who funded the study, that's a good chance to see if there's any kind of bias in the study. A self-interest study is a study that's funded by someone, and the results of that study make that someone look good. So Animal Rights Coalition coming up with a study that says people don't like real fur coats, that's in the best interest of the Animal Rights Coalition. So that's in their self-interest. So watch out for who funded it. They talk about funding. Chances are good it's the self-interest study option, the bias. And the other one's in here. Voluntary response is when people choose to respond. It could be a 1-900 number where they are paying money so that they can vote for, I don't know, TV, who wins the competition, or rate my professor is self-interest, a voluntary response situation. Non-response bias or missing data is, for example, a telephone poll. If people just don't answer the telephone, or if you send out the flyer for them to fill out and they don't send it back. Loaded or leading question is like the extremes. You either like math or you hate people. That's like, well, I don't hate people, so therefore I must like math. It's very often an either or situation, but it's a loaded question or a leading question that leads you towards one certain answer. Not fair. All right, question 8. Observational or experimental? A group of students are told to drink coffee while studying for a test, and the results are compared to a group not drinking coffee. Well, so the group not drinking coffee would be the control. The group drinking coffee would be the treatment. This is a controlled experiment. A placebo-controlled experiment, in this case, it would be students are told to drink coffee while studying for a test, and the results are compared to a group drinking non-caffeinated coffee where they didn't know, they couldn't tell the difference. Then you could test the results of caffeine on studying. This one is just drinking something, or I don't know if they're not drinking. So it is for sure an experiment. The placebo would have to be something where they're not sure what they're drinking. It could be the stuff, the treatment or not. And an observational study would just be you sitting in the testing center of the hall or wherever they are and looking for how many students are studying and drinking something. That could be an observational study. Question 9. A team of researchers is testing the effectiveness of a new HPV vaccine. They randomly divide the subjects into two groups. Group 1 receives an existing vaccine, and group 2 receives a new vaccine. So this is common when you're trying to find a drug or medicine that works better than the current drug or medicine that's being used. So this is not a placebo-controlled experiment because you can't, if there is a drug that is available that works, you can't give someone a placebo. That's not ethical. You have to give them what works and then test to see if something else works better. So this is an experiment. The existing HPV vaccine would be the control group. So that's group 1 would be the control group. Group 2, the new vaccine, that's the treatment group. And this is a controlled experiment. The control is the current standard care, and the experiment, the treatment group is the new standard care to see if it's any better. And then the blinding, neither the patients, so it's at least blind, or the doctors examining them. Now that's double blind, knew which group they were in, double blind. Blind is when the patients don't know, but the doctors do, and neither is when the patients know. You never let the patients know, but don't tell the doctors, so what's the point of that? Question 10, now we get into the describing data. Valeria categorized her spending for this month into these categories. This is a pie chart. If she spent a total of $2,900 this month, how much did she spend on fun? So fun is 16%. We want to figure out what is 16% of the total, the 2,900. Now, a lot of people are consistent with going from decimal, percent to decimal of is times, and that's great if you are. However, there's a lot of students that miss the decimal, and so I like to just let the calculator do it. This 16 per is divide, cent is 100. Let it work that out. Times 2,900 equals $464. That's how much money Valeria spent on fun. Okay, next up, we have a frequency table. So let me recreate this. I'm not sure why let's see if I can do it this way. Maybe. Very nice. So from this frequency table, we want to find the mean, first off. We know the mean is the sum over the total. To get the total, we can add up the frequency numbers, 3 plus 5 plus 3 plus 5 plus 2 plus 2 plus 2 plus 3. And just being careful, 3, 5, 3, 5, 2, 2. Oh, I missed a 2. 2, 3 twos, 3. There we go. Total is 25. That's the denominator. To work out the sum, we can recognize that if there are let's do this one. There are 5 4s. If we think about 5 4s, and we want to find the sum, we can do that easily with multiplication. So if we just multiply these numbers together, then we can add these numbers to get the sum, which is the numerator 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Just checking everything out. This will be the numerator, the mean. Let's add these together. 152. And now 152 divided by 25, 6.08. They should say 1 decimal place. They do not. However, the correct answer is 1 decimal place, 6.1. The general rule for the mean and median and standard deviation type of statistics is whatever the original test, the scores were. If there were no decimal places, you go to 1 decimal place. If there was 1 decimal place, you go to 2. If there was 2 decimal places, you round to 3, etc. Okay, next up, the median. Now I'm going to do this with the percentiles method that's used on the 5-number summary. The median is the 50th percentile. We work that out by taking 0.5 and multiplying by the total number of data. This would give us 12.5. Now the rule with the percentiles is if you get a decimal, whether it's 0.5, 0.1, 0.9, doesn't matter, you round up, always up. And this tells you to go to the 13th spot in the data, and that'll be the median. 13th spot, let's take a look. I have to add with the frequency numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm looking for the 13th spot. 12, 13, there it is. Oops. So 3 plus 5 plus 3 plus 5, 3, 5, 8, 9, 10, 11, plus 5 more. We're in a bunch of sixes when we get to the 13th. So the 13th one is a 6. There's the rounding. Had it second. That's a strange place for it. Okay. For the percentile method, if you get a whole number, then you do a mean. If you get a decimal, you round up. So if we got a whole number, say we did 0.5 and there were 24 of them instead, then that would be 12. Then that would tell us to do the mean. And we do the mean of the 12th one and the next one, 13th. So in this problem, the 12th and 13th were both 6s. So the mean of 6 and 6 is still 6. It wouldn't have changed the answer. But that's the general rules you do for the percentiles. All right, question number 12. Calculate the standard deviation. All right, step 1 is the mean. Step 2 is subtract the mean. Step 3 is square. Step 4 is quasi mean. Step 5 is square root. It's kind of a long process. We first do the mean. Let me just copy these numbers down. I do want them horizontal, or I just copy paste like I did before. This works better. Okay, so we're going after the mean first. So we need to add these up. Oh, that's not a plus. There we go. And divide by how many we just added up. 1, 2, 3, 4, 5, 6. There's 6 data points in this data set. Divide by 6, and we get the mean is 16.8. Okay, now one at a time, we subtract the mean from the 6 data values. So for example, we'd have 23.5 minus 16.8. That would give us 6.7. And 23.1 minus 16.8, this would give us 6.3. And 13.2 minus 16.8, negative 3.6, etc. Now, there's still some more to do, but I want to show you a way to speed this up a little bit, not a lot, but to show your work, this just takes some time. With the 6.7, for example, the next step would be square it, and then you get a number for that. And the 6.3 squared, 39.69. The problem with doing it this way is a lot of students do that on their calculator, and the square never gets to the negative, and they write a minus 12.96. That is not correct. At stage 3 of this process, none of these numbers should be negative. Parenthesis negative, oh yeah, that's right, 3.6 parentheses squared is the correct answer, but just a lot of students don't use parentheses, and then they get the negative and they forget that that should all be positive, and now all of this work in one mistake and they don't get the right answer. So let me demonstrate another approach. First off, if you're using this calculator, which is the one that SLCC recommends for the 1030, 1035, the TI-30XS, it has a nice mode called the math print mode. And it's pretty much always on when I use this calculator just because it's nice, it looks good. But it also has a store feature. So this is STO. And then you can store it in the button right above that in the X variable. The X doesn't mean the X like in algebra. This is just a storage spot. So now X is 16.8. So if I'm doing 23.5 minus X, it's a little bit faster to get that 6.7. But don't stop there. Square that answer by just hitting the square button. It takes answer squared, and whatever's in the previous answer, it'll square it, whether it's positive or negative, correctly. In this case, it gives us a fraction. Next button on this calculator is the arrow button. It converts from fraction to decimal, and sometimes decimal back to fraction. Depends on if it recognizes it or not. There's our 44.89. So look how much more efficient this is. 6.3 minus X. Oh, that's not an X. Oh boy. There we go. 6.3 minus X. Where did I get 6? Oh, ha, sorry. This number minus the mean. Let's try that again. 23.1 minus X is 6.3 squared, arrow, 39.69. 13.2 minus X squared. Because it's answer squared, it's going to take the negative and correctly square it. 12.96. Let's finish this now. 20.25. Showing your work, you actually don't have to show this middle row because that's a step towards the numbers you need to work with for step 4. So I would be okay if you don't list those if you were being graded by me. Subtract, square, 9.61, and 8.8 minus X squared, 64. A whole number, that's unusual. Okay. Next up is the quasi-mean. This is where we're going to add those 6 numbers up, but not divide by 6. That would be the mean. The quasi-mean is you always divide by 1 less than what you did in step 1. You divide by 1 fewer data points than there are in the data. Not 6, but 5. Always 1 less. The reason for this essentially is if we go back to the first picture I drew, there it is. If you wanted to know the standard deviation of the population and you did the standard deviation of the sample, without doing that divide by 1 less quasi-mean, the standard deviation of the sample is always too small. It just works out to be too small to give you a good idea of what the population's standard deviation is. If you divide by 1 less than the quasi-mean, then the standard deviation of the sample is enlarged so that it's much closer to, and in fact can be essentially used as, the standard deviation for the population. That's the math behind it, or the sort of math, explaining the math behind it. What we need to do is we need to add these 6 numbers up. Now, something else about this calculator. You can go and enter these numbers without having to type them all back in by just up arrowing until you get to the numbers that you're looking for and enter, and then add, and then go up to the next one. There's a point when you're like, this is not as fast as just typing them in, but it's nice to know you can do this kind of thing on this calculator so that you don't make any rounding errors or transcription errors. So this is the sum, 191.4, and we're dividing that by 5, quasi-mean, and we get 38.28. Final step, step 5, square root. Square root of the answer, 6.187. We had 1 decimal to begin with, so we can go with 2 decimals, 6.19. That would be the standard deviation. That is a lot of work, but that's how you do it. Hopefully that makes sense. Question 13. This is a box plot or a box and whisker plot. The whiskers are these lines that extend from the minimum to Q1 and from Q3 to the maximum. Those whiskers do not carry through in the box, so make sure that there's no line through there in the box. All right, the 5 vertical lines represent the 5 numbers in the 5-number summary. So we have 5, 9, 14, 18, and 20. This is a very simple question if you understand what you're looking for. Using box plots, you can compare between 2 different populations. So here we have Jenny makes the first quartile salary for a construction worker. So if we go to the construction worker, this first line is minimum. The next one is Q1. This is the first quartile. We go down and we see $40,000. So we see Jenny, $40,000. Okay. Marcos makes the third quartile salary for a teacher. Third quartile salary, there's the median. Third quartile, there we have 45,000. Okay, who makes more money? Well, Marcos does. How much more? $5,000. You could also say things like 25% every. So let's say the Marcos, what did he make? Third quartile for a teacher. So this third quartile for a teacher, let me do this. Copy that over. There we go. So if we're making the third quartile for a teacher, 45,000, every quartile is really a quarter of the population. So we can say that Marcos makes more than 25, 50, 75% of the teachers. He makes less than 25% of the teachers. Now, if we look up, the same line matches up with the median for the construction workers. So although Marcos makes 75% more than makes more than 75% of the teachers, he only makes more than 50% of the construction workers. And a Q1 construction worker makes more than 50% of teachers. So you can also use this, each quartile is 25% to answer those types of questions. All right, that completes this first review. This is the statistics review. This is not comprehensive. If you want a comprehensive review to really prepare for your exam, Go back over your homework. Do similar exercises, do them as many times as you feel like you won't get those problems wrong ever again, and you'll be very well prepared for the exam. Okay, probability. A die is rolled. So this is a six-sided die. Anytime they talk about a die is rolled or two dice are rolled, they're six-sided die. Find the probability of the given event. Write each probability as a simplified fraction. All right, the probability that the number is a 3. Well, there's only one 3 on a six-sided die, 1 over, and there's a total of 6 possibilities. So the fraction, simplified fraction, would be 1 over 6. What if the number is even? Well, on a six-sided die, that would be a 2, a 4, or a 6. So that are 3 numbers. 3 out of 6 reduces to 1/2. Make sure it's simplified fraction. Don't leave the 3/6. It will say something like it's equivalent, but not correct. Give me one moment. All right. The number showing is greater than 5. Well, on a six-sided die, there's only one number greater than 5. That's a 6. So again, 1 out of 6. All right, next up, Emma buys a bag of cookies that contains 4 chocolate chip cookies, 9 peanut butter cookies, 7 sugar cookies, and 5 oatmeal cookies. That adds up to 25 total cookies. So this bag has 25 cookies. What is the probability that Emma reaches in the bag and randomly selects an oatmeal cookie, eats it, and reaches back in and gets a peanut butter cookie? So this is without replacement. She ate that first oatmeal cookie. She did not put it back. So the first time she reaches in and gets an oatmeal cookie, there were only 5 oatmeal cookies out of the 25 total cookies. So the probability of getting that oatmeal cookie is 5 out of 25. The and is multiplication. Now, since she did not replace the oatmeal cookie, when she reached in for her second cookie, there were only 24 cookies total, and there were only 4 oatmeal cookies. However, she got a peanut butter cookie. There were 9 out of those 24 that were peanut butter cookies. Now let's take a look. They want a decimal, so we can go and create this with our calculator without having to simplify the fractions. 0.075. There's no rounding. That's the exact answer. See if it liked it. 2 decimal places, 0.08 would be the rounded answer. All right, this is without replacement. Now, had she put the oatmeal cookie back, then when she reached for the peanut butter, there'd still be 9, but then there'd still be 25. So if it's with replacement, then the sample space doesn't change. If it's without replacement, the sample space changes, and you just have to keep track of the smaller and smaller numbers as she picks more and more cookies. Question 3, marbles. There's only 16 numbers, so here's our jar of marbles. We have 10 red numbers, not red. There we go. And there's also 6 blue marbles. So let's just let those numbers represent the marbles. What's the probability that the marble is red? Well, there are 10 red numbers, red marbles, and there are 16 total. So we should get 10 out of 16 for that first one. Probability of red equals 10 out of 16. If they want simplified fraction, that would be 5/8. If they want fractions, which they do, 5/8 is 0.625, but they want us to round to 2 decimals, so therefore the 0.63. What about the probability of an odd? Well, since there's an equal number of odd and even, that should just be 0.5. But we could count them. 1, 2, 3, 4, 5, 6, 7, 8. 8 out of the 16, which again is 0.5. Now we get into the rules, the and or. Now there's two approaches. If you have the sample space, and I drew it, you can look for which ones are red or odd. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 are red. 1, 3, and 5 are also odd. That's 13 out of the 16 that are either red or odd. The calculator says rounded 0.81. Is 2 decimal places? Yeah, 0.81. But there's also formulas. The formula that's given on the exam for this is P of A or B equals P of A plus P of B minus P of A and B. So in this case, it would be P of red or odd would be the probability of red. Oops, I'll get there. Plus the probability of odd minus the probability of red and odd. Okay, what does that look like? Scroll down, there we go. Probability of red, there's 10 out of 16, plus the probability of odd, there's 8 out of 16. Those were our first two questions. We already had those answers. Minus the probability of red and odd. Which ones are red and odd? 1, 2, 3, 4, 5. What's really going on is we've counted up these 10. Then we've counted up all of the odd ones. Let's see if I can do this. There's the 10. And blue, there's the odds. And you can see that by counting up all the tens, all the reds, 10 of them, and all the odds, 8 of them, we've double counted the 1, 3, 5, 7, and 9 that are red and odd. That's why we have to subtract that 5/16 because we double counted. Add all that up, we get our 13/16, which is originally what we got. So you have the formula approach, but you also have, if you can see the sample size, just looking at this, sample space, just looking at the sample. Something similar happens with the and. Probability of blue and even. Well, we can just go through and look for all the blues and evens, and we see 3 of them. Those are the blues and the evens. Blue even, 3 out of 16. That's our answer. We can check 3 divided by 16. 0.8, approximately 0.19 if we go to 2 decimal places. But there's also a formula. It's probability of A and B equals the probability of A times the probability of B, conditional product, given A, conditional probability, sorry. That formula is a little bit different. The conditional probability makes it a little harder to think through, but essentially what we have is the probability of blue and even will equal the probability of blue times the probability of even given blue. So what this looks like is the probability of blue, well, there's 6 out of 16 times the probability of even given that they're blue. Well, if we're given they're blue, we're only looking at those 6. Out of those 6, what's the probability that they're even given they're blue? Well, there's 3 evens out of those 6. And this reduces back to the same answer we got. So the formula approach or directly counting from the sample space are both great and valid techniques. All right, moving on. Number 4. Same kind of thing, jars with marbles. 2 marbles at random. What's the probability they're both red? So red and red. And this is specifically at the same time, so you don't have a chance to replace the first one. So this is a without replacement problem. So the and is a multiplication, and that's our rule. However, we have a nicer way to do this, just thinking about it. The first time we dig into here, there's 15 red, total 15 plus 39, 54. There's 54 out in there. The next time we reach in, or at the same time, the second marble, there's only 14 reds left, and there's only 53 in the jar. 2 decimal places. Let's see if we get this right. Now this button has a fraction button. This calculator has a fraction button, which makes it nice to look at. So I'm just going to use the tools that I have and show you how to use them. It gives us a fraction. If they wanted the simplified fraction, that's it. Or we can convert to decimal. Now it's approximately 0.0733. And 2 decimal places, that would be 0.07. Okay, so without replacement, if you pick 2 things at the same time, you can treat that as picking one and then another without replacement. Question 5. This is now a 2-way table. All right, so check that call. Got it. Ready to go. The 2-way tables. This is a nice one to copy paste as well. Let's just go do that and that. Let's look at this situation. Right. If one student is chosen at random, find the probability the student was female or got an A. Okay. Well, or is essentially when we add the probabilities together. But here we have a 2-way table. So instead of the formula, we could just count them directly. Female or an A can include these 18 as well. Those 4 categories are either female or A. So doing it that way, we have the female ones or the additional A ones divided by the grand total, which we happen to have nicely. And that makes this a pretty easy problem to do. Let's do a fraction button. This is so nice to have this calculator because you can just see that what you have on your calculator is what you wrote down, and you know you're going to get this problem right. It's going to work it out correctly. I wish it would just do it right every time. But let's see, 0.901. Oh, they want 3 decimal places? Make sure to read that instruction set. If it shows up on the test, you're always going to be doing that, I hope. 0.901. Now, the other approaches, you could, of course, look at all the females plus the additional A's and add those up, and that's another way to get 64. Or all of the A's plus the additional females that weren't already counted, and that's 64. And then the formula tells you to add and subtract the double counting. So that would be the females, total females, 46. And I'm just looking at this column. It's easy, subtotals there. Plus all the A's, 32 out of 71. Subtracting the females with A's because these are double counted. If I look at this total includes the 14, this total also includes the 14. So I have to subtract that extra 14 that I double counted. And again, that's another approach to getting the correct answer. Question number 6. A test was given. All right, let's do it again. See what we get. All right. What's the probability that the student got a B given? Now, this is the conditional probability. That vertical line is given that they are male. So the term right after the given is the critical one to start with, or the thing right after the vertical line if you're given this notation instead. What you want to do is you want to think or highlight or focus on just the ones that are male. So that's this column, sorry, this row, and that's the only set of numbers that are involved in this probability. Given that they're male, you're in that green row. So the total, 39. And what's the probability you got a B? Well, those are 19 out of those 39. This is 2 decimal places, approximately 0.49. It's that simple. You want to look at this and the word or the category after the given, the vertical line, or after the word given, you want to just focus on those sets of numbers. Sometimes it's a row, sometimes it's a column, but just look at those numbers and answer with those numbers. There's a formula as well, but it's so much more complicated. And this is so easy, I don't usually even look at it. Okay, now the conditional probabilities, probability the person who tests positive actually has the disease, those are easy done with this two-way table. So I'm going to create a two-way table for question number 7 by simulating what happens with a virus on a town. So we know this is total, and this is total. These are subtotals, and down here's the grand total. There are 2 questions that show up. One is an incidence rate with the percentage, like this one, and another where they say instead of a percentage, like 1 out of every 500 people. If it's just a percentage like this, I always roll with a 100,000 person town. It makes the numbers nice and easy, no decimals in general. If it had said 1 out of every 500, then I'd run with 500,000. This is just a simulated town. We're going to let this virus run. We're going to test them all with the rates that they say and fill out this two-way table. All right, false, negative. All right, so we have positive tests and negative tests. We have the ones that are infected and the not infected. And now we just start to work through. Like this 0.6%, this is the incidence rate of the disease. This is giving us how many people are going to be infected. So the 0.6% is going to give us that spot. If you have a percent in this table, like we do now, and it's sitting in a row or a column, look for a total, and then you can apply them together. So this would be 0.6%, letting the calculator do the decimals, times the grand total, 100,000, gives us 600. 600 of those 100,000 people would be infected. And that's 0.6% incidence rate. Now we subtract from the grand total the 600, and we can see how many people out of that population were not infected. All right. Next up, we have the false negative rate. Okay, the first word they say is false. The second word they say is negative. The second one, and this is similar to the conditional probabilities, the second thing after the given or whatever, that's where you want to focus. So the negative rate is going to be in the negative column somewhere, or row, whatever, however you set it up. The false negative, which one of those is a lie? So you got a negative test. These people are infected and got a negative test. That's a lie. This is the false negative rate. This one down here would be the true negative. This is the false negative. Okay, once again, when you have a percent, look for a total, and then you can apply them. 8% of 600, and we can fill this number in. 8% of 600 is 48. 48 people of those 600 infected got a false negative. The rest of them got a true positive. They were infected, and the test said they were infected. That's true, and it was a positive test. Okay, last one. The false positive rate. Okay, the second word, positive, we're in the positives column. The false positive, which ones are a lie? If you have a positive test, but you're not infected, that's a lie. This is the false positive. This is the true positives. False positive rate was 5%. Okay, do we have a total? No. Do we have a total? Yes. We can apply that percent to the total. Let's see what we get. 5% times 99,400. This is how many false positives there were. 4,970. That's a lot of people that were not infected, and 5% of them is still a pretty good number of people. We can subtract those from the total that were not infected to find out how many people got a true negative. 94,430 of people were actually not infected and got a negative test result. Okay, lastly, we can add numbers to get the total. Here we have 5,522 and 48 plus the 94,430 is 94,478. And you might want to check those two sum numbers that you just got correctly add up to the grand total population. Everything looks great with this table. Everything's flying. Let's now look at what they ask. Compute the probability that a person who tests positive actually has the disease. Now we have to figure out, this is a conditional probability. What's given? What do we know about this person? Do we know they have the disease? No. The person who tests positive, that's what we know about them. They tested positive. So what's given about the person is that they got a positive test. What we want to find out is the probability that they actually have the disease. So we're looking for the probability of infected given a positive test. So the word after given, the word after the vertical line might also be the word after who tests, who, because that's a possessive. The person, they could have said this, what's the probability that a person has the disease given that they tested positive? But this is the other way that sometimes it's given. So be prepared to know which part of that sentence is the given words. All right. The given is the positive. This is the only set of numbers that we're using for this problem, which means the denominator is going to be 5,522, and the numerator is the infecteds of those, 552. 552 divided by 5,522 0.09996. And what decimal do we want? 3. So this would round up to 0.100. It does ask for 3 decimal places, so I am going to give it 3 decimal places, as did the correct answer. Very nice. All right, so in real world, this means if you got a positive test, there's only a 10% chance you were actually infected. That's kind of scary. False positives cost a lot of people a lot of time and money during COVID because they couldn't work. Okay, next up, here we have a sample space of a whole bunch of cards. This is a standard 52 card deck, which will be the type that you'll see on the test as well. The card is drawn randomly. Write the probability of getting a 6. Well, we can see there are 1, 2, 3, 4 6s out of 52. Let me demonstrate your calculator's tools. If you use your fraction button and hit enter, it'll reduce for you. That's nice. If you don't, and you just do a division, if you don't have this calculator, it will give you a decimal. Search for this button, the F arrow arrow D. Of course, we have a shortcut arrow arrow on this one, but you might not, but you should have that button. And it'll again have reduced your fraction for you. Okay, so if 1/13, 1 out of every 13 cards is a 6. The probability of not 6, there's a rule for that. It's 1 minus the probability of a 6. So that would be 1 minus 1/13. And without a lot of trouble, we can let our tool do the work and get 12/13. Now there's a much better, I don't know about better, but much cooler way to think about this. If one of the 13 are a 6, then the other 12 of the 13 are not a 6. This is the complement rule. I think it's E, not I, complement rule. What about a face card? Looking over here, we see 3 by 4. This part, 12 cards are face cards, ones with the faces. So probability of face card, well, that'll be 12 out of 52, which reduces to 3 out of 13. Well, if 3 out of every 13 are face cards, how many are not face cards? The other 10. Or you can do the 1 minus, and you don't need to use your calculator. You can do fraction work just fine. You've seen this all before, but it's nice to know your calculator has a backup plan for you. All right, running down to the end. Bag containing marbles. This time, this is an expected profit or loss, so expected value. It's important to see if the game costs money to play, because there's multiple approaches to this, and I don't know which one your teacher went over, so I'm going to show you all 3 approaches that I can think of right now. The book's approach is an awkward one, but it works. Your expected profit or loss, this is formula that will be given on the test, is the value to you, so you lose $1 every time you get a black marble. 28 out of, how many total are there? 28 plus 8 is 36, plus 4 more is 40. 28 out of 40 times, you're going to lose your $1. But you might get a gold, and that's $6 winning. And gold, there's 4 out of the 40. But wait, you don't win $6. Here's what the guy playing this game, like if I let you play this game and there's my money and my rules and everything else, you're going to give me $1. And then if you pick a gold, I only have to give you $5 because I already have your original $1 to give back to you. Or from your perspective, you started with $1 and ended with $6, and you can see that you won $5. Even though it says you win 6, you actually win 5. And then if you get a silver, you don't win 2, you win 1 because you get your original dollar back. And that happens silver 8 of the 40 times. So all of that together gives you your expected value. I don't know why I did that 1, but at least you can now see it's all entered correctly. Really, 0. That's very unusual. This is a perfectly even game. You play it forever and not win or lose money. Not usually a 0, but this is kind of random. This is the approach that I teach as well as the book's approach. So the book's approach is basically play, lose, win, win. Those are the different events that the book considers. You lose money a certain number of times, you win money a certain percent of the time, you win more a different way, etc. But I like to do the play, win, win instead. What that looks like is I'm going to consider that I lose that dollar 100% of the time. It's gone. I play to win, play to lose, whatever. I played the game, that money's gone. Now, I win $6 if it's gold. And it says I win $6. And I win $2 if it's silver. And it says I win $2. It's so much easier because the numbers match up and you don't have to do the subtractions or anything else like that. And -1 plus 6 times 4 divided by 40 plus 2 times 8 divided by 40 is still 0. It's working out. So that, I just think it's easier to set up, easier to understand. And then there's also simulation. The nice thing about running a simulation is it emphasizes what the expected value actually is. Instead of a formula that you like remember or not, it's what do you expect to win or lose. So this time we're going to pick every one. Okay, so the loss, the total loss is going to cost us $40 to pick all 40 marbles. The wins, well, we make, was it $6 for the 4 gold marbles? We're going to get all the marbles. We're going to get all 4 gold marbles because we're picking all of them. So we win 24 that way, but we also get $2 for the 8 silver marbles. So we get a total of $40. So the net, which is the wins minus the losses, is 40 minus 40, which is 0. And the expected value is the average. This is where you take the net and divide by the total number of the simulation, however many you played, how many times you played the game. All right. For some reason that was hard for me to say. It kind of weird because the answer is 0, but hopefully the way it's written, you can see why this works. How much money did you spend? How much money did you earn? What's your actual net win or loss? And then divide that by the total, and that's your average or expected value. All right, question number 10. Raffle tickets. A raffle ticket costs $2. What is the expected value to me, the ticket buyer? Well, I'm going to lose those $2 100% of the time. But I might win $98 if I get that one winning ticket. There's only one out of 140 that are a winning ticket. -2 times 1 plus 98 divided by 140. And this gives us -1.3. Now that's $1.03, which is a weird way to say it. Money, go to 2 decimal places. That's $1.30. Of course, they don't have it correct. They should have 2. It even says round to the nearest cent, and then they list it as dime instead of cent. It should have a 0. It accepts the 0 answer is correct, so they should just fix that. Okay, what if you purchase 10 raffle tickets? Well, if you lose $1.30 every time and you do that 10 times, you lose $13. You just multiply them. Now, what's the expected value to the PTO? That's the one selling the raffle tickets. If you expect to lose $1.30, who gets that? The PTO. You don't actually have to work out the other side. There's 2 sides of this situation, and it's the same money changing hands. If you lose $1.30, they gain $1.30. And now if they sell, why is this still highlighted? Stop. It's not, whatever. If they sell 140 tickets and they expect to make $1.30, we multiply that together and you'll see it's 182. I don't know why that, oh, why is my middle button stuck? Maybe that's what's wrong. Oh, that is obnoxious. My mouse just freaked out. Don't know what's going on with it. I can't just, I fixed it. I didn't. I cheesed it. There we go. 1.3, $182. That's how much they will make if they sell 140 raffle tickets. Beautiful. Last question. A company estimates that 0.9% of their products will fail after the original warranty period, but within 2 years of the purchase, with a replacement cost of $150. So they sell a 2-year extended warranty for an extra $10, so that if it fails within those extra 2 years, they'll pay you $150. So to the company, since this costs money to start, $150, let's see, it costs $10. The company makes $10 guaranteed. And then they lose $150, 0.9% of the time. And so here I have the percent as a divide by 100. 10 minus 150 times 0.9 divided by 100. 8.65. They expect to make $8.65 for every $10 extended warranty they sell. Now, for a change, the book approach, they make $10, not every time. If 0.9, so let's just look at the 0.9. 0.9 is 0.9%, sorry. 0.9% is 0.009. The rest of the time would be 0.991. That would be 99.1%. So they get all $10 almost all the time, not every time. And they don't have to pay you $150 because they use 10 of the dollars, the $10 you gave them, to offset that cost to themselves. And they only lose $140. So that's why they're not guaranteeing $10 a win. They're saving that $10 for in case something goes wrong. This is the books approach. It's a little harder to work out and think through, but it works. That did not work. There we go. And then you can also do a simulation. Let's do 1,000 policies. They sell 1,000 policies, so they make $10 for every policy. 10,000, that's $10,000. 0.009 of 1,000 is 9. So they lose $150 times the 9 times that happens. $1,350. So their net would be the 10,000 minus the 1,350. I did not do 10,000. Let's do that again. And that gives us, they make $8,650 if they sell 1,000 policies. The average is where they take their net and divide by how many they sold, and a third approach, getting us our $8.65. So multiple ways for the expected value. That completes the questions I was prepared for with the review. I hope this helps you prepare for your exam. Thank you so much, and good luck.